Hello everyone, this is the second part of chapter 1, Semiconductors. What are semiconductors? Semiconductors are materials whose conductivity is in between conductors and insulators. An example of a conductor is a copper, and an example of an insulator is glass. Okay? There are two types of semiconductors. One of the types is semiconductors made from single elements and semiconductor made from compound semiconductor. Now, you can create silicon or semiconductor from germanium element or the silicon element. There are two elements, either germanium or silicon. Now, silicon is used to manufacture or fabricate most of the chips, whereas germanium is used for most of the time it's used for light, such as LEDs. Those elements can be found in group number 4. Now, from the compound semiconductor, you can create semiconductors from gallium arsenide, and it's formed by combining elements from group 3 and 5 or group 2 and 6. Okay? Now, in this chapter, we're going to focus on the silicon semiconductor because, as I said, it's the one most used in chips and integrated circuits. Now, silicon, because it's in group number 4, it has 4 valence electrons and needs another 4 to complete its outermost shell. Now, this is the silicon atom. It has 4 electrons, the first, second, third, and fourth electron in its outermost shell. Okay. Now, in order for the atom to be stable, the outermost shell should contain 8 electrons. Now, in order for the silicon to become stable, we need another 4 for it to become stable. This is achieved by sharing one of its valence electrons with each of its 4 neighboring atoms. Now, see, this is the silicon crystal. Here's a silicon atom with 4 electrons. Okay, it needs another 4 to complete its outermost shell. Those other 4 are going to be shared from the neighboring atoms. So now they became 8. Now the silicon is stable. So here each pair of the shared electrons form a covalent bond. Each 2 electrons, they form a covalent bond. This is a covalent bond. Okay. This results in a pure or intrinsic silicon. Because here in the silicon crystal, all the elements are silicon. So it's a pure silicon. At low temperature is 0 Kelvin, all bonds are strong and no electrons are free to move to conduct electric current. Or at low temperature, the covalent bonds are strong. Okay, so the electrons are bound, they are not free to move. There are no electrons that are free to move to conduct electric current. That's at low temperature. So at low temperature, silicon is what? It's an insulator. There are no electrons to conduct electric current. At room temperature, there's enough energy to break some of the covalent bonds. So when some of the covalent bonds are broken, some electrons are free to move. So here, when a bond breaks, electrons are free to move and are available to conduct electric current if an electric field is applied. Now, in the pure silicon, there is equal concentration of electrons and holes generated by thermal generation. Thermal generation is the same as thermal energy. Now, in room temperature, we said some of the covalent bonds, they get broken, right? Now, when a covalent bond gets broken, an electron is free to move. When an electron leaves its parent atom, it leaves behind a positive charge. See here, it's illustrated in this figure. See, a bond is broken. Now, one electron has left its parent atom. It left behind what? A positive hole here. It says hole. Okay. Now, when it leaves behind the hole, another electron will be attracted to the positive hole, and it leaves behind a what? positive hole again. Now electron will be attracted by this positive hole, and here it leaves behind a what? Positive hole again. It's discussed in here. See, let's see. When electron hole leaves its parent atom, it leaves behind a net positive charge called hole. I just explained this. The charge of the hole, is equal in magnitude to the electron. Now, an electron from the neighboring atom may be attracted by the positive charge and leaves its parent atom. This action fills the hole that existed in the ionized atom, but creates a new hole in the other atom. As I said before here, when an electron leaves its parent atom, an electron gets attracted to this hole. Now, it leaves behind what? Again, a positive hole, which attracts another electron from another atom. Now, this process repeats itself with the result that we have a whole positive charged carrier moving through the silicon and is available to conduct electric current. Therefore, as temperature increases, more covalent bonds are broken. More electron hole pairs are generated. This increases the number of free electrons and holes, which results in an increase in conductivity in the silicon. Now, concentration refers to the number of charge carriers per unit volume, which is the free electrons or holes. What is the band gap energy? Band gap energy is the minimum energy required to break a covalent bond and generate an electron hole pair. Moving on. Now, the equal concentration. So in pure silicon, when an electron leaves its parent atom, it leaves behind a hole. So what is the concentration of electrons compared with holes? They are equal. Okay. The equal concentration of free electrons and holes generated by thermal generation in intrinsic silicon are too small to conduct current at room temperature. Because we said at room temperature only some of the covalent bonds are broken, so only few electrons are free to move, which are available to conduct electric current. Okay, carrier concentration and so the conductivity are strong functions of temperature. That's true. Why? Because we said as temperature increases, more covalent bonds are broken. When more covalent bonds are broken, then we have more electrons that are free to move. But this is a not desired property. It's undesired. Why? Because if the temperature decreases again, covalent bonds will be formed, and when they form, electrons are no longer free to move, so it becomes an insulator. Hence, how can we override this problem? We have to mix the silicon. We have to dope it. This will solve the issue. In doped silicon, the concentration of free electrons and holes are no longer equal as in intrinsic silicon. Doping, it involves introducing impurity atoms into silicon crystal to increase the concentration of either free electrons or hole. Now, let's see what kind of atoms should we introduce to dope the silicon. There are two atoms where you can dope into the silicon. One of the atoms is phosphorus, the other one is boron. Now when you fuse in phosphorus atom into the silicon, it results in an n-type silicon. Why n-type? I will discuss it in a moment. Now n refers to negative, p refers to, as you have guessed, positive. We get a p-type whenever we mix it with boron. Now as you see here, this is the silicon crystal. All silicons except one of the atoms, it's what? Phosphorus. This is phosphorus. Now phosphorus has a valence electrons of 5. That's the first one. Second, there should be one here. Third, fourth, and this is the 5th electron. Okay, so 4 of the electrons will be shared by the 4 other silicon atoms. Okay, and hence you have one that is free to move. So 4 of the 5 are occupied and the 5th one is already free to move. So at low temperature, all covalent bonds are strong. All electrons are no longer free to move except the one that's related to the phosphorus, which is free to move. So here, as you can see, at low temperature, you will still have one electron that is free to move. That is if you have used only one phosphorus silicon. Phosphorus atom. But of course, you're going to fuse many atoms, many phosphorus atoms. So you will be having many electrons that are free to move even at low temperature. So here, to increase the concentration of free electrons, silicon is doped with an element with a valence of 5, such as phosphorus. This results in an N-type silicon. The concentration of free electrons in N-type is equal to the concentration of the donor atoms. What is a donor atom? It's the phosphorus. Why? If you have, for example, one phosphorus atom, then you will have a free electron. If you have two phosphorus atoms, then you will have two free electrons. So that's why they are equal. The free electrons is equal to the donor atoms. Now, in N-type, the concentration of electrons is larger than holes. Why? Because phosphorus has a valence of 5. 4 is occupied. You have one that is free to move. Now, at low temperature, you have no electrons that is free to move, except that single atom of a single electron from the phosphorus. Hence, the electrons are more than the holes. Hence, named as N-type silicon. Negative. Okay? Because electrons are majority and holes are minority. Now, the positive charge associated with the phosphorus, the positive charge, which means the hole associated with the phosphorus atom, is bound charge. It's not free to move, which means that it does not move within the crystal. Clear? Let's move on to the p-type. How do we get a p-type? To increase the concentration of holes, silicon is doped with an element of valency 3. This results in a p-type silicon. Now let's see what happens. Boron has a valence electrons of 3. Okay? 1, 2, 3. And it has a positive hole. There will be a positive hole in here. Now this positive hole will attract an electron. See? It got attracted. What does it leave behind? It leaves behind a positive charge. Now, this positive charge will attract another electron, and it leaves behind a positive charge. This process repeats, okay? But now, as you have noticed, what's more, the holes or the electrons? Of course, the holes. There are only 3 electrons in the boron, and it has one positive charge. This positive charge will attract an electron from another neighboring silicon atom. Here, the concentration of holes in p-type is equal to the concentration of acceptor atoms. Why? Because if you have one boron atom, then you will have one hole. If you have 2 boron atoms, then you will have 2 holes, attracting 2 electrons from neighboring silicon atoms. In p-type, concentration of holes is larger than electrons. So electrons are minority and holes are majority. Hence the name p-type, positive. Okay, each boron atom has 3 electrons in its outermost shell. So it accepts an electron from a neighboring atom to form a covalent bond. This results in a hole in the neighboring atom and a negative charge in the acceptor boron atom. Okay, clear. Let's move on to and start giving you the equation related to silicon. Now, in intrinsic silicon, intrinsic silicon, intrinsic, we said it means pure. Okay, we have, let's choose blue. We have N is equal to P equal to Ni. What's N? N is the concentration of electrons. And its unit is centimeter minus 3. P is the concentration of holes, and the unit is the same. Ni is the number of free electrons and holes in a unit volume. Same unit, centimeter minus 3. Okay. Now, what is Ni? What's the equation for Ni? Ni is equal to bt 3 to the power of 3 to the power of divided by 2 exponential minus eg 2kt. Okay. Now, what's b? B is a constant. What's T? T is a temperature. Temperature in Kelvin. Okay. Eg is a constant. Same for K, constant. And T is temperature again in Kelvin. Okay. This is another equation. Okay. Now, the constants, they should be provided to you in the exam. B is 7.3 times 10 power 15, 1 over centimeter squared, K 3 over 2. Okay. E is 1.12 electron volt. And K is 8.62 times 10 power of minus 5 electron volt over Kelvin. Great. Let's take an example of Ni, how to calculate Ni. Let's go back to our work. Here you go. Okay. Let's paste the image. Paste it. Okay. Now, calculate the value of Ni for the silicon at room temperature. Which is T equal to 300 Kelvin, almost equal to 300 Kelvin. Okay. Now, Ni, as we said before, it's equal to what? It's Bt to the power of 3 over 2 exponential minus Eg over 2 kt. So it's Bt power of 3 over 2 exponential minus, did I add a minus? Yes. Eg over 2 kt. Now what's B? We said B is 7.3 times 10 power of 15. 7.3 times 10 power of 15. Temperature is 300. Power is 3 over 2 exponential Eg. What is Eg? 1.12. 1.12. And 2K. What is K? 8.62 times 10 power of minus 5 multiplied by 300 again. Okay. Now this will give you, or will give us 1.5 times 10 power of 10 centimeter minus 3. That's the answer. So whenever he asks us for Ni at room temperature, Ni is directly 1.5 times 10 power of 10. You can memorize this number. Okay? Moving on. Now, for doped semiconductors. For doped semiconductors. Or for doped silicon if you want. Doped is mixed, as we said before. We have two types of mixed silicons. We have a p-type and we have a n-type. P-type, how do we get a p-type? We mix it with boron. And how do we get an n-type? We mix it with phosphorus. Okay. N, what is N and what is P in both types? Now, for example, when the instructor asks you for N and P in both P type and N type, how are you going to clarify for the instructor that this N is referring to this P, for this type, and this N is referring to the N type. What we are going to do is we will add a subscript. For example, N subscript P, P subscript P, so it can refer to the P type. And here N subscript N, P subscript N. What is N subscript P? It's Ni squared over Na. And P subscript P is Na. N, the concentration of electrons in the N type is equal to Nd, and the concentration of holes in the N type is equal to Ni squared divided by Nd. Now what is Na and what is Nd? A refers to acceptors, it's an acceptor, and D is the donor, okay? Both Na and Nd are constants. They will be provided to you in the question. Let's take an example. Copy our page in here. Let's paste it. Paste. Okay. Go back to our pen. The question says, consider an N-type silicon. So he has identified the type of the silicon. So far we have 3 types of silicon: N-type, P-type, and the pure silicon, for which the dopant concentration Nd is 10 power of 17 per centimeter cube. Find the electron and hole concentration at T equal to 300. Now what is electron? It's the N. What is hole? It's P. And we are looking for the N type, so it's P subscript N, N subscript N. Okay? So what was the equation for N subscript N? Here. It was N equal to Nd, which is equal to what? 10 power of 17 centimeter per centimeter cube. Okay. And what is Pn? It's Ni squared divided by Nd, where Ni at room temperature, we said it's what? We can memorize the answer. It's 1.5 times 10 power of 10 squared divided by Nd. Nd is 10 power of 17. This will give us 2.25 multiplied by 10 power of 3 centimeter per centimeter cube. Okay? Those are the answers. It's easy. You just need to know the equations, the appropriate equations, so you can plug in. Now, I need to add one more page. Sorry. Okay. I need this page. Copy the page. Let's go back to our in here. I want to paste the page. Paste it. Delete this page. Okay. So now we have discussed the behavior of the silicon, whether if it's pure or mixed with phosphorus or boron. Now there are two ways for the movement. There are two ways for the movement of charge carriers so that the current flow in the semiconductor. You know, we said that when the covalent bond breaks, electrons and electrons are free to move. Now there are two ways for the movement. There's a drift current and diffusion current. Okay? When do we get drift current? We get drift current in uniform silicon bar. Okay? When electric field is established in the uniform silicon crystal, okay, we will have a drift current. Electric field always moves from positive polarity to negative polarity. You need to know the directions of electric field and holes and electrons based on this external voltage source. Holes moves with the direction of the electric field, whereas electrons moves in the opposite direction of the electric field. Okay. Now, because we have movement, we need to compare the Hall movement with the electron movement. Hall movement with electron movement. What is the Hall mobility? Hall mobility with the symbol mu p represents the ease of movement of holes through the silicon crystal in response to the electric field E. Whereas the electron mobility, represented as mu n, represents the ease of movement of electrons through the silicon crystal in response to the electric field E. Now, electrons are or move with a greater ease, so they have higher mobility than holes. Electrons have higher mobility than holes. Now, the flow of current is in the same direction as the positive charge. We already know this from our physics courses, and is opposite to the negative charge. Okay, great. Let's move on to the diffusion current. When do we get a diffusion current? Diffusion current occurs when density of charge carriers in a piece of semiconductor is not uniform. Carriers will diffuse from high concentration to low concentration. This diffusion of charge results in diffusion current. So we will always have the Hall diffusion fusing in the same direction as the Hall current, and the electron diffusion flowing in the opposite direction of the electron current. This is described in here. Okay? If holes diffuse from left to right, then the Hall current will move from left to right. Whereas if electrons diffuse from left to right, then the electron current will diffuse from right to left, which is the opposite. Okay, moving on. So we were discussing the drift current. What equations do we have in the drift current? Drift current. Okay, let's talk about the p-type and the n-type. Okay. The first equation is Vp drift, which is the drift velocity, which is equal to mu p multiplied by the electric field. Okay, so here this is the drift velocity, okay, which is equal to which the unit of it is centimeter per seconds. Let me highlight this, encapsulated in a green box. Okay, so what is the mu p? We just explained that mu p is a constant number and it's a Hall mobility. Not a constant number, it will be provided to you. That's what I mean. Okay, and E is the electric field. Now, electric field, if you want to calculate it, it's the voltage divided by the length of the silicon bar. In the n-type, V n drift is equal to the negative electron mobility multiplied by the electric field. Okay, mu n is the electron mobility. Okay, what's IP? IP is equal to A Q P Vp drift, and we just said that Vp drift is mu p multiplied by E. That's IP. IP is the current, the drift current. IP is the drift current with unit ampere. A is the area, Q is the charge, and P is the concentration of holes. Okay, moving on to the n-type. In is the same equation but with a negative. Qn Vn drift. Okay, so AQN Vn drift is minus mu n E. So minus with the minus, they cancel each other, right? minus with minus, they cancel each other. This will result in AQN mu n multiplied by E. Okay, that's IN. Let me highlight it. Let me put it in a box. Okay. Next, we have another equation which is JP. JP is IP divided by the area, or we can write it in the full form AQP mu P E divided by the area. Now area with an area, they cancel each other. This will give me QP mu P E. That's JP. So here now we have two more equations. What's JP? JP is the density. It's a drift current density. Drift current density with the unit A per centimeter squared. Okay? Doing the same for the N type, Jn is In divided by the area, and In is AQN mu n. Electric field divided by area. Area with area, they cancel each other out. So the resulting equation is Qn mu n E. That's Jn. Okay? Hope it's clear so far. Moving on. Now, we have discussed the drift current density for the P-type and the N-type. We also have the total drift current density. What is the total drift current density? It is the sum of Jp with Jn. Okay? Okay, great. So total drift current density is the sum of Jp with Jn. I don't want red, I want blue. Blue. Here. The total is Jp plus Jn, which is equal to Qp mu P E plus Qn un E. If we factor out Q and E, the resulting equation will become N mu n E. Okay, that's the total drift current density. Total drift current density. If you want, actually you can memorize. If you want to memorize it, you can just memorize this one. That's easier. Okay. Now this is the total drift current density. Okay. Now there's also another two equations for the total drift current density. It's JT equal to the conductivity multiplied by the electric field, and we also have total drift current density as electric field divided by the resistivity. Okay. Now if you want, there's no need to include this small t. You can just keep it like this. Okay. So those are two more equations. So if you compare this equation with this one, what is the conductivity? Conductivity is everything except the E, right? So conductivity should be this one. Let me write it in a clearer way. So conductivity is Q P mu P plus N mu N, and the resistivity is 1 over the conductivity, which is 1 over Q P mu P plus N mu N. Okay, this is the conductivity and this is the resistivity. That's conductivity with the unit A sorry, it's 1 over centimeter, actually ohm per centimeter. Ohm per centimeter. I know it's too many units, I'm getting confused also. Resistivity, that's resistivity, which is ohm per centimeter. Okay, let's take an example so everything becomes clear. Let's take an example so things become clear in here. Copy, let's go to our page. Let's go to our page in here. Let me paste it. Okay, let's see, what does the question say? Find the resistivity, so he wants the resistivity for pure, intrinsic and p-type with Na is given. Okay, use Ni, so I guess this is the room temperature, right? He gave me Ni, and assume that for intrinsic silicon mu n, so this is for intrinsic silicon, mu n is this and mu p is this. However, for doped mu n is this and mu p is this. Okay, let's start solving part A. For part A, we need the resistivity. What is resistivity for intrinsic? Now resistivity is 1 over q p mu p plus n mu n. Okay, what's q? You should know what's q. It's 1.6 times 10 minus 19. And p is, what's p? That's p for the pure. We already said that in pure, let me go back in here. In pure silicon, n is equal to p and it's equal to ni. So here, p is equal to n, it's equal to ni. And what is ni? Ni is 1.5 times 10 power of 10 centimeter per centimeter cube. So we'll plug this number in here, 1.5 times 10 power of 10. Mu p is, for intrinsic, it's 1350 plus n. What's n? Same as concentration of holes, 1.5 times 10 power of 10 multiplied by 420, the mu p of the intrinsic. Okay, this will give me 2.28 times 10 power of 5 ohm, don't forget the units, ohm dot centimeter, ohm multiplied by centimeter. Okay, that's for part A. Now we need to repeat this again, but for the p type. Okay, part B. Part B, p type. What is the resistivity there? The resistivity is equal to 1 over q p mu p plus n mu n. Okay, q is what? It's 1.6 times 10 power of minus 19. What's p? P is, that's p in n type. P in p type, so p subscript p. We said p subscript p has, it's equal to ni. Okay, so p subscript p is equal to na, which is equal to 10 power of 16 per centimeter cube. So here we're going to plug in the number multiplied by mu p for the doped, which is 400, yes. What did I do here? I think I swapped those two numbers, right? Here I should have written the mu p. Actually I written the, I think I have done a mistake. This should be 480 and this should be 1350, but it will give me the same answer. Okay, So for mu p, it's 400. It's 400 multiplied by n. What's n? N subscript p is n subscript p is ni squared divided by na. It's ni squared divided by na. So it's 1.5 times 10 power of 10 squared over 10 power of 16, resulting in 2.25 times 10 power of 4 per centimeter cube. Plugging in the number in here, 4 multiplied by mu n. Mu n is 1110. So we're done here. We just need to calculate the answer, and this will give me 1.56 ohm multiplied by centimeter. So I guess we're done for this question. I hope it's clear. Simple. As I said before, the only thing that you need to be careful of is to choose the correct equation. Let's take another example. Let me copy this. No, not this one, yes. Copy. Go back to my page. Paste it. Okay. So what does this question say? It says a uniform bar. So I guess, so as you have noticed, this should be drift current, right? Because you have a uniform n-type silicon, and the length is 2 micrometer. Has a voltage of 1 volt. Voltage is 1 volt. If nd is 10 power of 16. nd is 10 power of 16 per centimeter cube. Mu n is 1350 centimeter squared divided by volt per second. Find electron drift velocity. Let's do this. So what is the electron drift velocity? The equation for the electron drift velocity is, we need the electron, not the holes. We need the electrons. It's this one. So it's minus mu n multiplied by the electric field. Going back, so it's Vn drift is equal to minus mu n multiplied by the electric field. What's mu n? It's 1350. What's the electric field? We do not have the electric field, but we can compute it. We said earlier that electric field is volt divided by the length. What is the volt? It's 1. What's the length? Now it's 2 micrometer, but you need to be careful here. It's 2 micrometer, whereas all the other units are in centimeter. Actually, usually in silicon we prefer the centimeter. So we need to convert the micrometer into centimeter. How are we going to do this? We will say 1 meter is 100 centimeter. Okay, if 1 meter is equal to 100 centimeter, then what is 2 micrometer? You just multiply this number by 100. This will give me 2 times 10 power of minus 4 centimeter. Taking this number and plugging it in here will give me 5,000 volt per centimeter. 5,000. This will give me minus 6.75 multiplied by 10 power of 6 centimeter per second. Now, what's part B of the question? Part B says it needs the time needed for the electron to cross the 2 micrometer length. How can we compute the time? Actually, we'll use the equation from physics. Speed or velocity is equal to what? Distance divided by time. So time is equal to distance divided by speed. Now velocity is what? Speed with direction. But if we need time, we cannot put the negative sign, right? We cannot have a negative time. So we'll take the absolute value. The distance is 2 times 10 minus 4 centimeter. We said we need the centimeter rather than the meter. Divided by 6.75 times 10 power of 6. This will result in 30 picoseconds. What is pico? Pico is 10 power of minus 12. Okay? Side note. What's the next requirement in the question? They need the drift current density. Drift current density is Jn. Jn is In divided by area, or this equation. Now going back and looking at the question, you will notice that you do not have area, right? We do not have an area in the question, so we cannot use this equation. We are forced to use this equation, okay? The other one. So Jn is Q, it's Q n mu n multiplied by the electric field. What's Q? Q is 1.6 times 10 power of minus 19 multiplied by n. N is 10 power of 16. Mu n is 1350 and the electric field is 5000. Okay, this will give me 10.8 times 10 power of 3 a centimeter cube per centimeter cube. Okay, that's part C. Now for part D, the drift current in the case the silicon bar has a cross-sectional area of 0.25 micrometer square. Now we have the area. For part D, they need the drift current, giving that area as 0.25 micrometer squared. This is supposed to be micrometer square. Okay, micrometer square. So how can we calculate the current? We can calculate the current either using this equation or this equation. Now this I think will be easier. Why? Because we already calculated the Jn and we have the area, so we can calculate the In. We also can use this equation, but you will have to multiply all these terms together again, which will take time. I recommend using this equation. Okay, so it's Jn divided by area. Jn current divided by area. We're looking for the drift current, so it's Jn multiplied by area. What's Jn? It's 10.8 times 10 power of 3 multiplied by area. Now area, if you notice, it's in what? Micrometer square. We need to convert it to centimeter square, because as I said before, all of our units in the silicon are preferred to be in centimeter. Let me teach you how to do we convert from meter to meter square to centimeter square. Excuse me. 1 meter square is, so let's begin with the meter. 1 meter is 100 centimeter. We agree on this. Now 1 meter square is it's 10,000 centimeter square. Okay, our number is 0.25 micrometer square. Now here there's a trick. There's a little trick. Now you see here there's a micro before the meter square. What does this mean? It doesn't mean it's 0.25 times 10 power of minus 6 meters square. Here what's meant by the micrometer square is it's micro squared meter. It's actually micro squared. It's micro squared meter square. So you can think of it as there's a brackets before the square. This will give you micro square meter square. Now what does this mean? It means it's 0.25 times 10 minus 12, because powers, a power of 6 multiplied by power of 2 is it's a multiplication rather than power. So now we can convert this to centimeter square by multiplying by 10,000. This will give me 2.5 times 10 minus 9 centimeters squared. Taking this number and plugging it in the main equation will give me 2.5 times 10 minus 9, resulting in 27 microampere. Okay, awesome. We're done for this question. Now we have finished the drift current.